Hey everybody, welcome to my Calculus 2 Exam 1 review problems and solutions video. This is all about integrals, doing integrals, interpreting integrals, and applying integrals. We start with kind of a difficult integral to do. Integrate the square root of 16 minus x squared. Oftentimes when you've got the square root of x squared plus or minus something, it's a good idea to use a trigonometric substitution, no exception here. When it's of the form some number squared minus x squared, the best trigonometric substitution to do is x equals that number, a, times sine theta. In this case, a is 4 because 4 squared is 16, so this becomes x equals 4 sine theta. Why is this a good idea? We'll see how it works out because of trigonometric identities. We will use a fair amount of trigonometric identities to do this problem. We will need to differentiate this with respect to theta. dx d theta will be 4 cos theta. Then I'll pretend I'm multiplying both sides by d theta to say that dx is 4 cos theta d theta. That's going to be something that we need with the substitution method. We also will ultimately need to solve this equation for theta. I can divide both sides by 4 and write x over 4 equals sine theta. And then I can take the inverse sign of both sides to say theta is inverse sine of x over 4. It's also okay to write that as arc sine of x over 4. Either notation is okay. In fact, either notation is standard. Now we need to apply all this, and we're not out of the woods yet when we do so. We get the integral of the square root of 16 minus x gets replaced by 4 sine theta. 4 sine theta squared is 16 sine squared theta. Also, dx needs to get replaced by this right here, 4 cos theta d theta. Write that here. Now is where we use a trigonometric identity, the first one that we need. 16 minus 16 sine squared theta. Sorry that my camera is blurry sometimes. Hopefully that won't be too much of a problem, is 16 times in parentheses 1 minus sine squared theta. Then I can use a trigonometric identity. The fact that cos squared theta plus sine squared theta always equals 1 means I can replace this with cos squared theta. They are equal functions of theta. So this gives me ultimately the square root of 16, right there with the square root here. I'm assuming I've got the square root around this. That's 4 times another 4. That gives me 16. 4 times 4 is 16. I get the square root of cos squared theta, which technically speaking is the absolute value of cos theta. But what we'll see is if we go ahead and make the assumption that cos theta happens to be positive, we get the right answer anyway. Ultimately, what's happening when we do that is we get ultimately two situations where we choose cos theta to be positive, giving us the right answer. And if we had chosen cos theta to be negative, there would be another situation where we take a negative square root and we would ultimately get the same answer in the end anyway, but we don't really worry about it. Don't forget about the cos theta right there. That 4 was already taken care of with the 16. And we can write the integral like this. And yes, once again, assume cos theta is positive. It does give us the right answer in the end anyway. It's an assumption people can make and get the right answer. So this is the integral of 16 cos squared theta d theta. Now at this point, you've got two choices. You can use integration by parts, which is fine, and you're going to have to use integration by parts twice, in fact. And in the end, when you get an answer, you're going to use the fact that theta is inverse sine of x over 4 and draw a right triangle to help you simplify things in terms of x. Or you can use a trigonometric identity right away, and this is the way I prefer. However, this does have the downside that you need another trigonometric identity before you can do your simplification. So it's a little tricky either way you do it. I'm going to go ahead and replace cos squared theta with 1/2 plus 1/2 cos 2 theta. That is a trigonometric identity. That equals cos squared theta, no matter what theta is. It is a useful identity for integration because now this integral is fairly easy to do. You will, if you need multivariable calculus, in other words, calculus 3, need to use that kind of identity a fair amount in calculus 3. So it's good to know. Anyway, I can distribute the 16 through there. 16 times a half, of course, is 8. Integrating 8 with respect to theta just gives you 8 theta, so I can write in 8 theta. And I can also say I'm going to replace that theta with ultimately inverse sine of x over 4, or again, you could write arc sine of x over 4. I also have 8 cos 2 theta that is being integrated. Now, technically speaking, to do that kind of integral, if you want to be extra careful, you could do another substitution, say u equals 2 theta. However, it's simple enough that you really should be able to do it in your head with perhaps a little experimentation. What you'll ultimately get is 4 sine 2 theta. Then don't forget your plus c. Why? Well, you can always check by differentiation. Differentiate this, you'll get 4 cos 2 theta times 2 because of the chain rule. 4 times 2 is 8. Yes, that matches 16 times 1/2 being 8. It does work. However, again, if I'm going to simplify this, I need another double angle formula. This one right here was based on a double angle formula for cos 2 theta. There's a double angle formula for sine 2 theta that says it always equals 2 sine theta cos theta, no matter what theta is. The sine theta can be replaced by x over 4, but I will need to figure out what cos theta is in terms of x, and this is where drawing the right triangle is ultimately what you want to do. You can think about it with a right triangle, or you could use a trigonometric identity. For some harder problems, it's typically easier to think about it with a triangle. Draw a right triangle, label one of the non-right angles with theta. I'll label it this one, but I could have done that one. And then you want to remember SOHCAHTOA, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We know the sine of this angle is x over 4. So, opposite over hypotenuse. Therefore, I can take the opposite side to be x and the hypotenuse to be 4. Of course, there's other choices too. I could have taken this to be 2x and that to be 8, or 3x and 12, or 4x and 16. It doesn't matter, but you might as well take the simplest thing possible. Then we're going to need to find the cosine of this angle adjacent over hypotenuse. Therefore, we need the adjacent side. Use the Pythagorean theorem. I'll leave it to you to figure it out, that you'll get square root of 16 minus x squared, and it's not a coincidence that that matches what you see there in the integral there. So the cosine of this angle is going to be adjacent over hypotenuse, square root of 16 minus x squared all over 4. I can now simplify to my final answer. Again, the theta there gets replaced by inverse sine of x over 4, like that, which again you can also write as arc sine of x over 4. They mean the same thing. Plus, ultimately we have 4 times 2 is 8. We also replace the sine theta with x over 4, and replace the cosine theta with square root of 16 minus x squared all over 4. 4 times 4 is 16. 8 divided by 16 is 1/2. The final simplified answer is 8 inverse sine of x over 4. That's supposed to be a negative 1 there. Plus 1/2 x square root of 16 minus x squared plus c. Don't forget your c. There we go. We could check it by differentiation. It's not terrible, but it does take a little while because you end up needing to get a common denominator to add some fractions and simplify. I'm not going to take the time to do it. On to problem number 2, which is the same function that's being integrated, but now it's with a definite integral from 0 to 4. We could, in theory, use the answer we got from number 1 to evaluate this thing exactly. It's actually quicker to realize the graph of this function is, well, for this interval, it's a quarter of a circle of radius 4 centered at the origin. That's something you can figure out if you didn't know that, just by looking at it. And therefore, its area is 1/4 pi r squared. It's a quarter circle. What's the radius? Again, it's 4, so we get 1/4 times pi times 4 squared is 4 pi is going to be the area of this quarter circle, which is also going to be the value of this definite integral. But the point of this problem is to approximate this definite integral using rules, ultimately the trapezoid rule with n equal to 2, the midpoint rule with n equal to 2, and Simpson's rule with n equal to 2, and we'll also compute errors in these approximations. Now I need to let you know that the way I'm going to show you to do this is different than many books do. with regard especially to the trapezoid rule and Simpson's rule. I'm going to use what our textbook calls an empirical approach, where rules for trapezoid and Simpson's rule are based on averages, and they're motivated by looking at errors and relative sizes of errors and relative signs of errors in situations where your functions are always, say, decreasing in concave down like this, or always increasing in concave up, and that kind of thing. What am I talking about here? Well, we're getting there. First, what is the setup? We have the interval from 0 to 2 that we're talking about. 0 is the left endpoint, that's the A. This is A. 2 is, 0 to 4. 4 is the right endpoint, that is B. And we are going to use two subintervals, n equals 2, of equal size, delta 2, x equals 2. So the first interval goes from 0 to 2. The second interval goes from 2 to 4. This is also called x0. This is also called x2. The midpoint there is called x1. x1 equals 2. All right, that's the basic setup that's going to allow us to compute the left-hand sum, the right-hand sum, average them to find the trapezoid sum. We will also need to evaluate the function at the midpoints 1 and 3 to help us evaluate the midpoint rule. All right, let's get going. What does the left-hand sum do? For each subinterval here, the first and second one, you take the left endpoint and go up to the graph to determine the heights of the approximating rectangles. So for example, the left-hand sum is going to give you the sum of two rectangles that look like this, the sum of their areas. And it will be, you can see, too big because the function's decreasing. Let's go ahead and see what it gives us. Before doing so, maybe it's good to just go ahead and evaluate the function at all the values of x that will need it. F of 0 is the square root of 16 minus 0 squared. That's nice, and that's 4. We will need to evaluate the function at 1 and 3 for the midpoint rule, so let's go ahead and do that. F of 1 is square root of 15. We'll go ahead and use a calculator here. Let's go as fast as we can. 15 is the square root is about 3.872983. Let's use 6 decimal places of accuracy as we go, and then we'll round to maybe 2 or 3 at the end and hope that our rounding errors have not compounded enough to make that off. That should be fine. 3.87, oops, I forgot a 7 in there. 3.87, that's a 7 there. 2983 is the value of f at 1. Yes, double checking. Okay, that looks good. F of 2 is going to be square root of 16 minus 4 is square root of 12. 12 to the 1/2 power is about 3.464102. If I round to 6 places after the decimal. F of 3 is going to be square root of 16 minus 9 is square root of 7. 7 to the 1/2 power is about 2.645751. And finally, f of 4 is nice. That's square root of 16 minus 16 is square root of 0 is 0. All right. Let's use these things. Let's see. Let's put the work down here maybe. The left-hand rule with n equal to 2 is going to be symbolically, I'll just write it symbolically for this first one, f of 0 times delta x plus f of 2 times delta x being 2, right there. So this will be approximately 4 times 2 plus, use this value right there, 3.464102 times 2. Let's go ahead and write what this is because we'll need it for the right-hand sum as well. 3.464102 times 2, 6.928204. That gets added to 8. The value of the left-hand sum is about 14.928204. I'm really hoping I haven't made any mistakes. If I do, I'll maybe try to make a note of it. Right of 2, we'll take this value here, right there, and add on f of 4 times delta x, but f of 4 is 0. So we're just going to get 6.928204. Okay? The left-hand sum is going to be too big. The right-hand sum is going to be too small. And averaging them certainly seems reasonable to give a better answer, and that's what the trapezoid rule does in this empirical approach. Again, this is not the quote-unquote standard formula. It's left 2 plus right 2 divided by 2. I'm going to average these past two answers here. So we have 14.928204 plus 6.928204 divided by 2 is approximately 10.928202. What about the midpoint rule? For the midpoint rule, we want to use the function values at the midpoints 1 and 3 here, and also multiply by delta x equals 2. We're still finding areas of rectangles. The trapezoid rule can be interpreted in terms of areas of trapezoids, and in fact the midpoint rule even can be interpreted that way, but we're not going to take the time to do that. So again, this was 3.872983. Let me just again double check that I didn't make a typo there. 15 to the 0.5 power, 3.872983. Yep, okay, times 2 plus the next one there, 2.645751 times 2. Let's just get the answer here. This times 2 and then plus 2.645751 times 2. Looks like it's about 13.03746869. Okay, I'll round that to 13.037469. And then finally, it turns out that the midpoint rule typically does about twice as good as the trapezoid rule in terms of the magnitude of the errors. And they, at least in simple situations like a concave down graph, they typically have the opposite signs. So what you end up doing with Simpson's rule in this empirical approach is doing a weighted average of the midpoint in trapezoid rule, where the midpoint rule gets twice the weight. So we multiply the midpoint rule by 2 and the trapezoid rule by 1. And then we divide by 3. Okay, so here is the midpoint answer. I'm going to multiply that by 2. Then I'm going to add the answer from the trapezoid rule, the 10.928202, and I'm going to divide that by 3. The Simpson's rule is giving about 12.334379, which will round to 334,380 when I go to 6 decimal places. I could round further. I'm just wanting to not lose accuracy there. Yeah, I definitely could round further. And in fact, I think for part B, I will round further just to save time. After errors in these approximations, this is part B. Using the fact that the exact value is 4 pi, though, is approximately 12.566371. And I also want to use the fact that error in general is actual value minus approximate, and I always remember it that way because that goes in alphabetical order. So we're after the error, not for left and right rules, but for trap and mid and simps. So the error for the trapezoid rule is the actual value, 12.566371, minus the approximation from the trapezoid rule, 10.928202, and I'll just round that. Let's see, 1.928202 to about 1.64, say. A positive error when you have an underestimate. It turns out the error for the midpoint rule will be the 12.566371 minus the value from the midpoint, 13.037469, and that will be approximately what here? 12.5664 minus 13.0375, I'm rounding more here, is about negative 0.471. Did I make a mistake? Is that right? Hopefully that's right and I haven't made a mistake. It's doing even better than twice as good as that one unless I've made a mistake somewhere. And then finally the error in Simpson's rule, the actual value 12.566371 minus the number that comes from Simpson's rule, 12.3344, say. I'm worried that I made a mistake because that midpoint rule did so much better than the trapezoid rule. Hopefully I did not. I'll make a note on the video if I did. All right, on to the next problem. The next problem is less computationally intensive. A basic differential equation. Solve this initial value problem, okay? Real basic differential equations here at the beginning. Later in the course, we'll do more complicated differential equations. Something really simple like this just is saying, find a function whose derivative is always that, and goes through that point, okay? It's an integral. All you have to do to solve this is integrate this function, 2x squared plus 3x plus 4, and you'll get an answer that involves a plus c, and you got to figure out what c is based on the initial condition. We're just trying to get the idea of a differential equation in the most basic situation when we know a function's derivative. There are more complicated kinds of differential equations. This is just another antiderivative problem with an initial condition. So do the integral, you're going to get 2/3 x cubed plus 3/2 x squared plus 4x plus c. Then use the initial condition when x is 0. Y is 2 is what that means. 2 equals y of 0 equals 0 plus 0 plus 0 plus c when I plug in a bunch of zeros. So c equals the initial value of y. That doesn't always happen. You got to be careful. It doesn't always happen. And what this means is the final answer is very quick. Combine these two things. Y equals 2/3 x cubed plus 3/2 x squared plus 4x plus 2. That is the unique function that solves this initial value problem, IVP, which is a differential equation along with an initial condition. If I did not have the initial condition, I'd just write that and I'd call it a general solution. It would represent infinitely many functions. On to number 4. This function, capital F of x, is defined by an integral where the variable in this problem is the upper limit of the integral. Fundamental theorem of calculus is what we need here. Yes, we're finding derivatives. Capital F prime, capital F double prime, and this strange derivative, well, we'll think about it. We'll need the chain rule. And ultimately, we're going to need to figure out where capital F of x is going to be concave up. Now, you might wonder, especially looking with this minus sign there, is do we ever take the square root of a negative number here? The answer is we don't. If you set this quadratic under the square root equal to 0, you'll see that it doesn't have any real solutions. And in fact, because the coefficient of t squared is positive, this quantity under the square root is always a positive real number. If you want confirmation, the quadratic formula would give ultimately a complex roots to it. So you don't have to worry about this going negative. And that's worth noting for part B, it turns out as well. Looks very difficult, but it's actually a very easy problem to do because of the fundamental theorem of calculus. Our book calls it part 2. Second fundamental theorem of calculus. Many books call it part 1. Differentiating an integral where the variable is in the upper limit of the integral. All you have to do is just write down the same function that you're integrating and replace the dummy variable, integration variable, with the variable that's up there. So replace the t's with x's. And that's all you have to do. That's all there is to it. That is the answer. That's amazing. You don't actually have to do the integral, so to speak, before you differentiate it. The point is differentiating the integral, the derivative and integral sign cancel out, so to speak, okay? Which is always true when the function you're integrating is continuous and is a nice thing to know, especially when you can't figure out an antiderivative. You still can say what the derivative is of this function, and you can ultimately evaluate values of this function by numerical integration. All that's just background stuff. So anyway, there's the derivative. We need the second derivative as well. So now we just used ordinary calculus rules, in this case the chain rule. Bring down the 1/2. We got x squared minus 2x plus 2 to the negative 1/2, and then multiply times the derivative of the inside function, which will be 2x minus 2. And we can simplify this a little bit to x minus 1 over the square root of x squared minus 2x plus 2. Okay? That's how it simplifies, and that'll be handy for part B because we want to figure out where f is concave up. Where is this thing positive? We'll come back to that. With the derivative of f of x squared, before I can use the FTC, I need the chain rule in abstract form. The inside function is x squared, the outside function is capital F. So this is the derivative of the outside function, plug in the inside function, and multiply times the derivative of the inside function. But what is capital F prime? It's this thing. I'll bring the 2x in front, so I get a 2x times square root of this thing where you replace each x with x squared. So I get x squared squared is x to the 4th minus 2 times x squared plus 2, and that is the answer for that derivative. I'm doing things that are theoretically complicated pretty fast here. You need to know your facts pretty well to do these fast, but it does make sense if you've practiced this kind of stuff before. Where is capital F of x concave up? It would be where capital F double prime of x is positive, which would be equivalent to this fraction being positive. And just like I mentioned at the beginning of this problem, the thing under the square root is never negative here when x is a real number. So the sign of this thing is completely determined by the sign of the numerator. So the answer here is f double prime is positive when x is bigger than 1, and that is where f of x itself is concave up. Now we're not going to try to draw the graph of f of x, and in fact it would be difficult to do without in your calculator because it's defined in terms of an integral. But I will tell you, if you can use technology ultimately to graph it, you would see it's concave up when x is positive, bigger than 1, excuse me, and x is concave down when x is less than 1. On to the next problem. Evaluate these definite integrals. And I made them kind of challenging, maybe not as challenging as the very first problem, but still kind of challenging. This one, I hope you've practiced enough to know you to use integration by parts with. This one, maybe not so clear. You might try integration by parts, but if you've practiced enough, you know this kind of thing actually involves substitution. For one thing, if you let your new variable be square root of x, x to the 1/2, the derivative of that will be 1/2 x to the negative 1/2, and hey, we have a square root in the bottom that's related to x to the negative 1/2. Many books call the substitution u. Our book calls it w. Doesn't matter. I'm going to let w be square root of x, or x to the 1/2. And that means we need to figure out dw. dw dx is going to be 1/2 x to the negative 1/2. And then if I pretend I'm multiplying both sides by dx, I can say dw is 1/2 x to the negative 1/2 dx. This, if I multiply by 2, is saying 2 dw is 1 over square root of x dx. And that tells me I can replace the dx over square root of x with 2 dw. If I convert to the new variable, and if I want this definite integral to stay a definite integral that is equal to the original definite integral, I must, and I emphasize this very heavily with my students, change the limits of integration. And also, if you do so, make sure you stay with the new variable. Don't go back to the original, okay? With x equals 0, it's easy. Square root of 0 is 0. With x equals pi squared over 4, well, it's still easy, but make sure you make the change. Take the square root of pi squared over 4 to get pi over 2. You must change that if you want to say write an equal sign here. Now you could do it by finding the antiderivative first and then going back to x and keeping the original limits of integration. But it's good to know this. Don't forget to replace 1 over square root of x with 2 dw. So there's a 2 cos of w in here, dw. Do this integral to get the right answer, and you never have to go back to x. You're going to get 2 sine of w, evaluated from 0 to pi over 2. That'll be 2 sine pi over 2 minus 2 sine 0. 2 times 1 minus 2 times 0 is 2. There's your final answer, a nice final answer. This one involves integration by parts. And when you use integration by parts with definite integrals, you do not change the limits of integration. You keep them as they are. A little funny here, it's just one function, it seems. Well, you want to think of that as function as 1 times the function. You want to always let v prime be something fairly easy to integrate. That's the first rule of integration by parts. Arctangent of x is the integral we're trying to do, so don't let v prime be arctangent of x, it must be the 1. That means the u must be the arctangent of x, which also could be written as inverse tangent of x. U prime then will be 1 over 1 plus x squared, and v will be the integral of v prime will be just x. Okay, many books you would write dv here equals dx, and you'd say v is still x. And here you'd say du is 1 over 1 plus x squared dx, if you've got a book that does that, but our textbook does this notation. The formula says do u times v minus the integral of v times u prime with respect to x. And so you end up multiplying these things on the main diagonal, and I forgot my limits of integration here. and these are limits of integration for x. Get everything in terms of x. So you got the product of these two things, x times arctangent of x, evaluated from 0 to 1, minus the integral from 0 to 1 of the product of these two things, x divided by 1 plus x squared. This thing becomes 1 times arctangent of 1, which is just arctangent of 1, minus 0, minus this integral. This integral technically you could do by a substitution. W equals 1 plus x squared would be the one to do, and then dw would be 2x dx. But you also could really do it by guessing, and you'd guess hopefully 1/2 natural log of, well, you can write an absolute value sign in here, but you really don't have to because 1 plus x squared is always positive. I'll write one anyway, it doesn't really matter. Arctangent of 1, you could try it with your calculator and see what it approximates to, but you really should know it equals pi over 4, 45 degrees. You always want to use radians though. And then this thing, you're going to get 1/2 natural log of 1 plus 1 squared is natural log of 2, and then minus 1/2 natural log of 1 plus 0, natural log of 1. Natural log of 1 is 0. Natural log of 2 doesn't really simplify. You get pi over 4 minus 1/2 natural log of 2. That is the answer. You could approximate it, and you could check it by, numerical integration on your calculator, for example, that this is correct. All right, that would be what this answer is. On to page 3. I think this is page 3. This is an application to probability. Maybe you've done applications to probability, maybe you haven't. If you haven't and you aren't interested, you could go on to the next problem here. But it is an interesting application. T is the wait time in seconds for the next car to enter an intersection. What in the world is that? That's called a random variable. Cars come into intersections at random. It's modeled by randomness. It's a continuous random variable, and it's got what's called a probability density function, PDF, equal to this function here. This is typically a type of model that's fairly accurate for waiting times for example, cars coming into intersections or other kinds of wait times. Part A, find the cumulative distribution function, CDF, capital F, for this function. These things are valid when t is greater than or equal to 0. These functions are going to end up equaling 0 when t is negative because we're not thinking about t taking on negative times here. The notation is suggestive here. Capital F is going to be an antiderivative of little f, but it's not going to be any old antiderivative of little f. It's got to go, since time starts with 0 here, through the origin. Its graph has to go through the origin. So probably the quickest way to do this is to just do an indefinite integral of the function that we're starting with. We could write this as a definite integral, but it gets a little tricky. Get a plus c, and then we want to make sure the graph goes to the origin. And here the c will not be 0 like the differential equation problem. Anyway, you do this integral, you're going to get negative e to the negative 0.25t plus c. Okay, you could check that with the substitution. And then you want, so that's going to be the capital F of t. You want capital F of 0 to be 0, essentially because we can't have negative wait times is the reason for that. Integrating the density function gives you probabilities, and capital F, this cumulative distribution function, turns out to give you probability. I'll explain that more in a little bit here. But we want F of 0 to be 0. In this case, that means c will not be 0. We'll get negative e to the 0 plus c must be equal to 0. This is a negative 1, and this means then c is positive 1. Add 1 to both sides. And therefore, capital F of t is positive 1 minus e to the negative 0.25t. That is your cumulative distribution function. Let's go ahead and say what this represents in terms of probability right away. This represents the probability that the wait time, capital T, is less than or equal to the given number, little t. It's a little bit strange to look at. P stands for probability. Capital T represents the wait time of the next car. How long will you have to wait till it reaches the intersection? T, you want to imagine to be some fixed number like 1 or 2 or 2.7 or 3.49. This function gives you that probability. It is always an increasing function, and its graph looks like this, and in fact approaches 1 as t goes to infinity. As this wait time, little t, this number you pick, gets bigger and bigger, You're almost guaranteed that the car is going to come through the intersection by that amount of time, is the idea there. Okay, that's called the cumulative distribution function. You could write this as a definite integral. I won't do the definite integral, but I encourage you to try to think about it this way. You could write this as a definite integral from 0 to t, where the variable is in the upper limit of the PDF, little f, with respect to some new variable. I like using Greek letters here, like tau, little f of tau d tau, and try doing that definite integral, thinking of little t as fixed, and you should ultimately get the same answer. I'd encourage you to try that on your own. Part B, find the probability that you'll have to wait between 3 and 5 seconds for the next car to enter the intersection. Probability that capital T is between 3 and 5. In the abstract, you always want to think of that as the integral of the PDF, the little f, from 3 to 5. And by the fundamental theorem of calculus, that's always an antiderivative at the upper limit minus the value of the antiderivative at the lower limit. Now that capital F does here happen to be an antiderivative, and so we could use it. However, we could use other antiderivatives to do the integral as well. Plug in t equals 5 there, you get negative 1.25, excuse me, 1.25. And plug in t equals 3, and you'll get e to the negative 0.75. Ultimately here, the 1's cancel, the c cancels. So you really ultimately get e to the negative 0.75 minus e to the negative 1.25 for this probability. And let's go ahead and approximate that. E to the negative 0.75 minus e to the negative 1.25 is approximately 0.1859 for this probability that you'll have to wait between 3 and 5 seconds. Graphically, it's the area under the PDF between 3 and 5. It's that kind of area. That gives you the probability that you'll have to wait between 3 and 5 seconds. And this principle holds in general. The integral of the PDF, the area under its graph, gives you the corresponding probability. And by the way, the area under the entire graph, the entire PDF, as you go from 0 to infinity, an improper integral ends up equaling 1, and you should check that as well. Part C says find, use a different color here. Part C says find the mean wait time. By definition, essentially the mean, also called the expected value of the random variable, is the integral of the variable, in this case t times the PDF, over the entire domain where the PDF is positive, which goes from 0 to infinity. So this is going to be an improper integral that we'll have to do, unless you happen to have memorized the mean for this type of PDF, which you may or may not have done. And I am emphasizing in Calculus 2 that I want my students to write improper integrals using limit signs to emphasize the meaning of them and the fact that they could converge or diverge. This one is going to converge in the end. Unfortunately here, it's kind of a bit of a pain here to do this improper integral. We are going to need integration by parts. We could let u equal 0.25t and then v prime be the other thing, e to the negative 0.25t. Either choice would be okay in terms of v prime being easy to integrate, but in this case you do want u prime to be something simpler than u, a constant. So that's why this is a good choice. When you integrate that, you'll get negative 4 e to the negative 0.25t. So keep the limit sign in front. Limit as b goes to infinity of u times v is 0.25 times negative 4 is negative 1. Negative t e to the negative 0.25t going from 0 to b. Minus the integral of the product of these two things. Two negatives will make a plus. And again, 4 times 0.25 is 1. So we'll get this. Plug in, let's be careful, plug in the b and the 0. We'll get negative b e to the negative 0.25b minus, plug in 0, you get 0. And then with this integral, you'll get a negative 4 e to the negative 0.25t going from 0 to b. This limit is going to be 0. L'Hopital's rule can be used to confirm that. We got a linear growth times an exponential decay. That's just something to know. So ultimately we get the limit as b goes to infinity of, let's see, plug in t equals b there. You get negative 4e to the negative 0.25b minus what you get when you plug in 0. This is going to go to 0 as well, and in the end you get plus 4 times 1 is 4. The mean is 4. And it's not a coincidence, and that'll be in seconds. It's not a coincidence that that happens to be the reciprocal of the number in front, which matches the number there, except there was a negative sign. It's not a coincidence that that happens. 4 seconds is the mean. Theoretical average wait time for the next car to come into the intersection. Part D is to find the median wait time, the middle value, you might say, for data. If you've got like 25 data points and you list them in order from least to greatest, the middle value would be the 13th data point, it turns out. But this is more of a theoretical mean because it's based on the setup with these PDFs and CDFs. And you want to figure out where the CDF equals 1/2. That's going to be the median. Okay. Again, the CDF here represents the probability that your wait time is less than or equal to a given number. We're wondering what wait time will make that probability equal to 1/2. That's what the median is by definition. You might want to call this T sub m for median there. So we go ahead and plug in the formula for the CDF. I'm again going to use a T sub m. Maybe I could just use an m instead, but I guess I'm stuck with T sub m right now. And you want to solve this for T sub m. You'll need to take a logarithm. Negative 0.25 times T sub m will be the natural log of 0.5. And so T sub m will be negative 4 times the natural log of 0.5, which is a positive number. And I hope you know from properties of logs, this would be the same as positive 4 times natural log of 2. 4 times natural log of 2, about 2.77 seconds. Okay, that would be the median wait time. It is less than the mean. This is a right-skewed distribution. Sometimes you have very high outliers, which tends to make the mean higher than the median in this kind of situation, if you know some basic statistics. I know I'm going fast in all this. It's because there's a lot of problems to do, but I hope it's beneficial for you anyway. Next problem. Some approximations to the integral for the various numerical approximations with n equal to 2 are given in this table, and the errors. The true value of the integral is this number. Okay, so this is related to this empirical approach to numerical integration. Part A, use what you know about errors and use the errors for n equals 2 to estimate the errors for n equals 20. And by the way, you can check in each case, actual value minus approximations does give you the corresponding error. So I'm trying to fill in this column first here. And the principle is, with the left and right hand rules, when you increase n by a factor of 10, the error goes down by a factor of 10. So what that means for left and right hand rules is we can write these same numbers with the decimal point 1 spot to the left. Now, that's probably too many significant digits that I'm doing here because it doesn't typically, it's a rough rule of thumb here to say this. So we're probably not going to get exactly those errors, but roughly speaking, we would, and we're still illustrating the principle that the error goes down by approximately a factor of 10 with the left and right hand rules. On the other hand, with the trapezoid midpoint rule, when the amount of work, the value of n goes up by a factor of 10, the errors go down by a factor of 10 squared, by a factor of 100, and that means you need to move the decimal point to the left 2 spots. So for the trapezoid rule, we're going to get 0.00191031, and for the midpoint rule, it'll be negative 0.0, add 2 more zeros, 0.0099078. And finally, for Simpson's rule, when we increase n by a factor of 10, the error goes down by a factor of 10 to the 4th. 10,000, wow. Move the decimal point to the left 4 spots. So after the decimal, you're going to get 4 more zeros. Keep the negative sign there. There's 2 of them, and add 4 more, and we get this. Not only is Simpson's rule better for fixed values of n, it gets better a lot faster as n increases, is the big idea point of all this. Part B does the integrand function, in other words, the function you're integrating, appear to be increasing or decreasing, concave up or concave down, explain with words and pictures. For sake of time, I'm only going to draw pictures and verbally explain. If you're my student, you should write brief explanations based on these pictures. We did see with the second problem here, where is it here? That with this function, back in the second problem, the function was decreasing. The left-hand rule was too big and the right-hand rule was too small. That happens with decreasing functions. Is that going on here? Yeah, the left-hand rule is too big, the right-hand rule is too small. This function is going to be decreasing. And the graph was concave down. In that situation, the trapezoid rule tends to be too small and the midpoint rule tends to be too big. And you can draw pictures that explain that, and I will. Trapezoid rule is smaller than the midpoint rule. Yeah, this appears to be concave down. Here's your generic decreasing function, decreasing. I didn't make that one concave down or concave up. I made it a mixture. Left-hand rule is too big, negative errors. And right-hand rule is too small. Right-hand rule would give you areas of rectangles that look like this instead. Okay, so it's decreasing. And then concave down, it turns out, I could draw it either decreasing or increasing. I'll draw it decreasing to be consistent with this one. It turns out the trapezoid rule gives you areas of trapezoids whose tops are secant lines. And when the graph's concave down, those secant lines will be underneath the graph. And so the trapezoid rule is too small and has positive errors. Turns out the midpoint rule, even though it's initially defined in terms of areas of rectangles, can be thought of as in terms of areas of trapezoids as well. But there are trapezoids where the top of the trapezoid is a tangent line instead of a secant line. And when your graph's concave down, that's going to be tangents that are above the graph, and your trapezoids will have areas that are too big. Midpoint rule is too big here, negative errors. So there's a quick verbal description with pictures of the reasons, and my students, you should write brief explanations of a sentence or two in each case. Number 8. Find the volume of a solid over a certain region, that's the base, whose cross-sections perpendicular to the x-axis are semicircles. Fixed type of cross-sections here. Semicircles in this case, sometimes you encounter problems with square cross-sections, sometimes with discs, in other words, circles, sometimes with equilateral triangles, for example, is another type that you might encounter. Make sure to draw a three-dimensional picture or a head-on cross-sectional area. I will draw both as part of your work. Okay, so what are we doing here? What's this region, first of all? Okay, I'm going to draw a three-dimensional picture to start with. This is not a solid of rotation where you might want to draw a two-dimensional picture to start with. So I'm going to imagine this as being the x-axis going this way, coming out of the paper, so to speak. The y-axis is going into the paper, and the third axis, call it a z-axis, is going up like that. X goes from 0 to 2. Y goes from 0 to x cubed. In other words, you want to draw the graph of y equals x cubed. Say about like that. 2 cubed is 8. I'll label that an 8, though we won't need it. What we're describing here is this region right there. That's the region defined by those inequalities. And we're defining a solid, a three-dimensional object, whose base is this region, and whose cross-sections perpendicular to the x-axis, if you cut the cross-sections with a knife, perpendicular to the x-axis, are semicircles. Like, for example, there's an example of one semicircle that is perpendicular to the x-axis. That's one of the slices. Another slice might look like this. Another one looks like this. They get smaller and smaller as you go toward x equals 0 because that's the distance there. The diameter of the semicircles has to get smaller and smaller. The biggest one is when x is 2, and it looks like about like that, say. And the solid we are creating has those cross sections, and this is an approximate picture of it here. We're trying to find the volume of that. There's a three-dimensional picture. The head-on cross-section, which you could also draw, is a semicircle. Sort of imagine that you're over here and you're looking straight on toward that, and you see one of the slices that looks like a semicircle. We want to find the volume of this thing. Now, A couple different approaches people often take to this is they imagine Riemann sums, thinking about slicing this and thinking about thin slices with a certain width delta x, and they write that the volume of such a thin slice, delta v, to be approximately its cross-sectional area, pi r squared over 2, because it's a semicircle, times its small width, delta x. Delta x represents the small width of that. You'll see approximate equations looking like this, and then they'll say the total volume is approximately the sum of these little volumes, which is approximately a sum like this, pi over 2 r squared times delta x. And then they'll let delta x go to 0 and get an integral, though we need to do something else too before we can actually do the integral, and I'm not saying what that is quite yet. I will also say that some people take an even more informal approach to this and imagine this width to be an infinitesimal width called dx, or dx, and imagine instead of delta v to be a small volume, an infinitesimal volume, call it dv. And essentially it's the same kind of thing, except you think of this as an exact equation instead of an approximate equation. And you think of v right away as being a summation of things like this, where the summation is really represented by an integral sign. And you might write some sort of equation like that, okay? These are very, very hand-wavy kinds of things. This is not rigorous math. Don't ever think this is rigorous math that we're talking about here. The point is to try to get to the integral that we want to evaluate as quick as possible. Now, in doing all this, you are going to need to, again, do a definite integral in the end, and you are going to need to figure out how r, the radius of the semicircle here, depends on x. But that's easy. The diameter of the semicircle is this distance at an arbitrary value of x. It's that distance there. It's the second coordinate of that point. Well, it's the second coordinate of this point minus the second coordinate of this point. Now, the second coordinate of that point is 0, the y-coordinate. The y-coordinate of this point is, well, y, but it's also x cubed, because that curve is y equals x cubed. So the diameter here is x cubed, and that means the radius is x cubed over 2 in this example. For another example, it could be different. In the end, your total volume is going to be the integral pi over 2 times r squared. That'll be pi over 2 times x cubed over 2 squared. X cubed is the diameter, so x cubed over 2 is the radius. With respect to x, what are the limits of integration? It's based on the region here. X goes from 0 to 2. That is going to be the volume of this. We can pull out a pi over 8 and integrate ultimately x to the 6th from 0 to 2. Pi over 8, we're going to get an x to the 7th over 7, evaluated from 0 to 2. That's going to be 2 to the 7th times pi over 56. 2 to the 7th, I'm going to do that in my head, 128 pi over 56, which does reduce, what, to 64 pi over, what would it be, 28, 32 pi over 14, 16 pi over 7. I hope I have not made a mistake. Again, if I make a mistake, I'll put it on there. 16 times pi divided by 7 is approximately 7.181, say, if I have not made a mistake. All right. I do compute these things ahead of time, but I forget the answers. I think this was right. I don't see a mistake. Again, I'll make a note if there is a mistake. On to the next problem. Find the volume of another solid. This time it's a solid of revolution, obtained by rotating a region in the two-dimensional plane between y equals 1 and y equals x squared for x between 1 and 5 around the x-axis. And I could make it harder by revolving around some other horizontal line, or maybe even some vertical line. That would make it even extra hard. Not after an extra hard problem here. Make sure you draw either the three-dimensional picture or the head-on cross-sectional area. And again, I will try to draw both, but I'll start with a two-dimensional picture of this region. Y equals 1 is a horizontal line. Here's the x-axis. This is y equals 1 here. Y equals x squared is going to look like this. Say 1 is there. It's going to go way up pretty fast. Okay, so this is not really to scale. x goes between 1 and 5. Y goes between 1 and x squared. This is the region that we are now going to imagine rotating around the x-axis to get a three-dimensional solid. And this solid will have a hole in the middle because of the fact that the bottom of this region is not the x-axis. It's going to have a hole in the middle that's not going to be counted as part of the volume. It's going to be some sort of weird looking thing like this. Maybe you can make an instrument that looks like this. I don't know. What are the cross sections going to look like if you slice this perpendicular to the x-axis? Take a knife out and slice it. And remember, there's a hole in there. The cross sections are going to be like this. These cross sections are the regions between circles, the sometimes called washers. A washer as in what you would put in on something to put a screw through. You could also maybe call them an annulus or an annuli, plural for annulus would be another name that you could give to this. A ring, be another more informal name. I guess washer is informal as well. But the key thing is the cross-sectional area in terms of x. Well, you're going to need to figure it out in terms of x, but there's an outer radius and an inner radius, r sub out and r sub in. We're going to need to figure out how those depend on x, but the cross-sectional area is the outer circle's area, pi r sub out squared, minus the inner circle's area, pi times r sub in squared. That'll be the cross-sectional area quantity. We'll need to figure out how it depends on x using the nature of the region. And we'll ultimately integrate that. If you wanted to think in terms of Riemann sums, we've got this thin washer there with a certain width there, delta x. You could write delta v as approximately pi r out squared minus pi r in squared. That's the cross-sectional area times the width delta x, and you could say v is approximately the sum of those things. And as you let delta x go to 0, you're going to get an integral. We could also think in terms of infinitesimals. In the end, you're going to get the volume to be the integral of this kind of thing. I can bring the pi out, where r out and r in depend on x. How do they depend on x? Think about this picture here. The x-axis is the center of the washer, so to speak, corresponding to the middle here. R out is the distance between the x-axis and the upper graph. That's the x squared. So you get x squared squared. R out is x squared. And R in is the distance between the x-axis and the inner one, which is constant. It's 1. The outer radius changes as x changes, it increases, and the inner radius stays constant. And x goes from 1 to 5 here, 1 to 5. So we're going to get pi times the integral from 1 to 5 of x to the 4th minus 1. So we'll get 1/5 x to the 5th minus x. X going from 1 to 5. And now you just don't want to make a mistake. So this is pi times, 5 to the 5th over 5. That'll be the same as 5 to the 4th minus 5. Minus plug in 1. You get 1/5 minus 1. Hopefully no mistakes. 5 to the 4th. 625 minus 5. 620, and then minus negative 4/5 is plus 4/5. Hopefully no mistakes. As a fraction over 5, 620 times 5 is 3100. Pi times 3100 plus 4 over 5. 3104 pi over 5. I'm not feeling so confident. Divide by 5 and then multiply by pi. It's about 1950. Boy, I'm not feeling confident. I feel like I made a mistake. Again, I'll make a note if I've made a mistake. I don't intend this video to be perfect. I make plenty of mistakes. I hope I didn't make a mistake here. I think everything is okay, but I just feel like this is maybe not quite the right answer. Maybe I should check it by doing 620 plus 0.8. At least check my fractions here. times pi. Okay, I guess that's okay. Integration's okay, I think. Okay, I think this is right. I just don't feel very good about it. Anyway, on to number 10. We're getting close to being done here. Mass density of a thin rod is this thing in grams per centimeter when x is between 0 and 3. Find the total mass and find the center of mass. Thin rod, that's actually meant to be like a wire, a thin wire. Laying along the x-axis, say, from 0 to 3. There's our thin rod or wire. It's not a constant density. Now this density is a little strange. This is it's called a linear density. It's not mass per unit volume, it's mass per unit length. That's because it's a simplification because we're imagining the rod or the wire is so thin that we can effectively treat it as a linear object. If I graph this function above the wire, so to speak, it's measuring the density. Where it's higher, it's more dense. Okay, the atoms are more packed closely together, and they're less closely packed together where the density function is smaller. This is actually related to and similar to probability density functions. Not the exact same thing, but it's similar and related to it. Anyway, as far as finding the total mass of such a rod, you just integrate the density. That's all you have to do. It's pretty easy. Intuitively, you imagine chopping this up into little pieces of width, say delta x, and you would say the small mass of such a little piece is approximately the value of the density there times the little length. This is in grams per centimeter, and this is in centimeters, and therefore this total is in grams. And then you'd add those up to get the total mass and ultimately get an integral. The answer for part A, is to integrate the density function from 0 to 3. So doing it is fairly easy. And you're going to get 1/3 x cubed plus 4x going from 0 to 3. 3 cubes 27, divided by 3 is 9. 9 plus 12, and then a minus 0. Looks like 21 grams is the mass of this thin wire. Okay, this thin rod. I'm pretty sure that is correct. What's the center of mass? Turns out for the center of mass, before you can compute it, you have to compute something called the second moment. This is related to a mean for probability. Second moment is to integrate x times the density. I'm not explaining why, or why it's called not a second moment, but a first moment, a moment. It's related to the idea of a moment of inertia, but like why do they call it a moment? It's kind of confusing. It's ultimately related to the law of the lever. You can look into details of the derivations. Anyway, we're going to integrate x times this thing will be x cubed plus 4x. That's not going to be the final answer, though, when we do this. We need to do something else. We're going to get 1/4 x to the 4th plus integrate 4x. You'll get 2x squared from 0 to 3. 3 to the 4th is 81. 81 fourths plus 3 squared times 2 is 18, and then a minus 0. Getting a common denominator of 4, we'll have 81 plus 18 is the same as 72 over 4, and that'll be 153 over 4, I believe. 4 goes into 150 how many times? That goes into 120, 30 times. I'm having trouble. Okay, pressure's on. 153 divided by 4. 38. Okay, this is 38.25 for the moment. But this means the center of mass is actually the moment divided by the mass itself. So it's 153 over 4 divided by 21. It's 153 over 84. And that is the same as this thing, 38.25 divided by 21, about 1.82. Units for the center mass would be the units of distance. Yeah, it's a position here because it's the location. This is center of mass. And this is centimeters. Okay, same symbol there. Centimeters. The center of mass for this rod is to the right of the middle value, the middle value being halfway between 0 and 3, not the median. 1.82 is right about there, which makes sense because the rod is denser closer to 3 and less dense close to 0. So that is what we end up doing for the center of mass, okay? Last page. Two more problems. This one is one that I like to do in Calc 2, though not every Calc 2 class will do it. We're ultimately going to find arc length of a curve, but it's a parametric curve. You may be doing arc length of regular graphs of regular functions instead. But I like doing parametric curves. I got parametric equations, f of t equals t, g of t equals t to the 3/2, representing x and y coordinates of a motion of some object in the xy plane for t going between 0 and 4. Use your calculator to help you. I will just draw a picture of the curve, the motion, on the set of axes below. Draw some vectors of something called a position vector and a velocity vector for this situation, based on I teach my students how to do this. And ultimately find something called the speed function, or confirm it equals this, and the distance traveled, which is the same as the arc length as an integral of the speed. So it's a very physical kind of thing that we're trying to do here. So you can certainly use parametric mode in your calculator to plug these things in and see the graph. I'm just going to imagine plotting some points. In this particular scale, when t is 0, certainly you're at the origin. These functions have a value of 0 when t is 0. When t is 1, x is 1, and y is 1 to the 3/2, which is also 1, so we're right there at 1, 1. When t is 2, we can certainly approximate 2 to the 3/2. Maybe I should do that. 2 to the 3/2 power. It's about 2.83. When t is 2, x is 2, and y is about 2.83. So which brings us right around here or so when t is 2. When t is 3, 3 to the 1.5 power is about 5.2, and x is 3. So we get about right here when t is 3. And when t is 4, we got x is 4, and y is 4 to the 3/2, which is 8. So we end up right around here when t is 4. And so you can see the distance is getting further and further apart here. The object is speeding up, and the graph is a curve. Kind of looks like a parabola, but it's not. Motion along the curve is toward the northeast there. As far as vectors go, the position vector at time 4, just is an arrow that points from the origin to the location at time 4, just an arrow like that. That's not the curve of motion, that's just the displacement of the object, measuring the change in position from time 0 to time 4. The motion itself is along the red curve, not the green arrow. And then we can draw the velocity vector after maybe doing a calculation as well. We should probably figure out what the velocity vector is. It's going to be, you want to draw it to start at the location of the object and be tangent to the curve. So it's going to point up this direction. Turns out, how do you find the velocity vector? Turns out it's going to be f prime of t for the first component, it's called. That's written times I hat, which is an arrow that points straight to the right with a unit length, plus g prime of t, the derivative of the y coordinate with respect to time, times something called j hat, which is an arrow that points straight upward with unit length. If you don't know what those are, don't worry about it. F prime of t is 1. G prime of t is 3/2 t to the 1/2. And if I plug in t equals 4, the velocity vector is going to be I hat plus square root of 4 is 2. 2 times 3/2 is 3. And what this ends up meaning is that the arrow that I would draw for the velocity vector has what's called a horizontal component of 1 and a vertical component of 3. And so if you draw it to start here, you go over 1 and up 3. It's an arrow about like that. So this green one's the position vector, often called r, and this purple one's the velocity vector, often called v, and little half arrows are often put above the vector. So just a little bit to know about vectors. I don't teach much beyond that in the Calculus 2 course. If you know some physics, you'll know more about vectors. Part D, the speed function is this, and you can confirm that calculation. I'm not requiring my students to do that. And the distance traveled is this as a function of time, also giving you the arc length of the curve as a function of time. The directions say use this substitution to help you evaluate this integral. Make sure you change the limits of integration, just like we did back a while ago, page 2, I think, to help us show our work appropriately. So the speed function here, or the distance traveled, is this integral, the speed of tau d tau. So I take this thing and replace the t with tau. You should use a different letter there. And here's the substitution we use. This is going to mean dw is 9/4 d tau, which will also mean d tau is 4/9 dw, and we would make that replacement. This gets replaced by w, so it becomes square root of w, or w to the 1/2. The d tau gets replaced by 4/9 dw, and I also need to change the limits of integration using this equation right there. When tau is 0, this equation, there's a 9/4 there, sorry that I kind of wrote over it, becomes 1 plus 0, 1. And when tau is t, this gives 1 plus 9/4 t. 1 plus 9/4 t, yes, there's going to be a t up there. It's not just a plain t, it's a 1 plus 9/4 t. Now do the integral. The 4/9 can just stay there. You get a w to the 3/2 over 3/2, which is same as multiplying 2/3 times w to the 3/2. W goes from 1 to 1 plus 9/4 t, and yes, that is a t again, I emphasize. No, not a tau anymore. This simplifies to 8/27, and then I'd have 1 plus 9/4 t to the 3/2 minus 1 to the 3/2. 8/27 can be multiplied through if you like, but I can also just leave it out here. This is fine. This is the distance traveled function. Okay, this is dist of t, also giving you the arc length of the curve as a function of time, which is the same as distance traveled for a motion. And this could be graphed and analyzed, and if you differentiate it, you will get the speed. So it's a worthwhile exercise to do. Last problem. Oh, it's a proof. Use the comparison test to carefully prove that this improper integral converges. Okay, it's not technically a difficult proof in the big scheme of things, but you got to say things in the right way. And what is the comparison test? You need to know that. You might want to look it up. I'm just going to go ahead and write the proof right away in sort of a formal way. Of course, when you're trying to do this thing, you need to practice, and you need to do some scratch work typically to rethink about it ahead of time. But for sake of time, I'm just going to write the proof right away. What we want is this, let's call this function f of x. We want to compare that function to some other function g of x, whose integral like this we know converges. By the way, I could have started the lower limit at 0. I chose 1 because it's just going to make it a little easier in terms of the comparison test. But I could have started at 0. This function does not have a vertical asymptote or anything at 0. The impropriety, so to speak, is the infinity. So we're going to let f of x be this function, 1 over cube root of 1 plus x to the 6th. I don't want to integrate that function. In fact, I had Mathematica do it before I made this video, and it was not a pleasant thing to look at. It involves something called the gamma function. Crazy, crazy, crazy. And I want to let g of x be a function that I can compare this to that's always going to be bigger than f, and whose integral is going to be known to converge. And ideally, you want to pick g to be something simpler. What would be an example of something simpler, whose integral I would know converges? Well, you got to know some things, but one thing that would make this simpler is to get rid of that plus 1 there. Maybe I should let g of x be 1 over the cube root of x to the 6th, which is the same as 1 over, okay, I'll be careful here, x to the 6th to the 1/3, and I multiply those exponents to get 1 over x squared. And g, because it doesn't have the 1 in the bottom, is certainly bigger than f. I'm dividing by something bigger to define f than I am for g. The function f is smaller than the function g. Its graph is below the graph of g. So if the area under the graph of g is finite, the area under the graph of f will be finite. And you should know the area under the graph of this thing, as x goes from 1 to infinity, is finite. And that's why I picked the 1 there, by the way, instead of a 0, because that has a vertical asymptote at 0. So, okay, how do I keep going here? I should note that f of x is positive, not negative here. F of x is certainly positive for all x in the domain of integration greater than or equal to 1. Also, since 1 plus x to the 6th is greater than or equal to x to the 6th, no matter what x is, but certainly for all x greater than or equal to 1, that implies that, well, the cube root of 1 plus x to the 6th is also greater than or equal to the cube root of x to the 6th, which is x squared, for all x greater than or equal to 1. So their reciprocals have an opposite relationship with the inequality. The greater than or equal to becomes a less than or equal to. So f of x, which is the reciprocal of cube root of 1 plus x to the 6th, is less than or equal to 1 over x squared, which is g of x for all x greater than or equal to 1. We know, by know I'm saying if you're doing this kind of thing, you should know this, or your professor should tell you, you can use this, that the improper integral from 1 to infinity of g of x, which is the improper integral from 1 to infinity of 1 over x squared, converges. That's a known fact that people commonly use in this kind of proof. When the power, often called p here, is bigger than 1, this kind of integral will converge when it goes from 1 to infinity, or 2 to infinity, or 3 to infinity. Not 0 to infinity, though. Or 0 to 1, or 0 to 2 for that matter. It's when it's some positive number here to infinity. If that power there, often called p, is bigger than 1, this will converge. If it's less than or equal to 1, it will diverge. But we want a convergent one. Therefore, by the comparison test, for improper integrals, the integral we're interested in is the integral of the f of x converges as well. Okay, QED. Again, intuitively, the graph of f is below the graph of g. They both do have the same value when x is... No, they don't have the same value when x is 1. Okay. This is f. That's g. If the area under the graph of g is finite, then since the graph of f is below it, the area under the graph of f will be finite even as you go out to infinity here. It's an infinite extent region, but the areas can be finite. These improper integrals do converge. Proofs are logical arguments. Even though it might seem silly to you, it is worthwhile, I think, to practice at giving logical arguments like this. But you have to do it in kind of a formal way when you're first learning it. Thanks for watching.